Okay, so now we pass to another part of this chapter. We will also use space curves, their arc length, etc. at some points. So we review some of the fundamental properties. Okay, so a parametric curve so in our case, in the plane, to begin with, is given as x equals a function of t and y equals another function of t. Okay, so these are parametric equations. And here, t is in some interval. So this interval can be a finite interval, or it may be all of the real line. Okay. So our basic examples will be, well, we will have, okay, some examples. X equals cosine theta, let's change t to theta. Y equals sine theta. Okay. So we can say theta is between 0 and, say, pi over 2. Okay. So basically, sometimes you try to eliminate theta and understand this, because sometimes we understand Cartesian equations. Sometimes it's better to look at these parametric equations. So that's why we have different ways of looking at these things. Now, this we know is part of a circle. And this part, the interval, tells us whether we are taking all of the circle or not. And direction is important, because we start from this point when theta equals 0. This gives us a point. As theta is increasing, we are moving along the curve. So these parametric equations carry one extra information other than x squared plus y squared equals 1. This also gives us direction. So that will be important in the way we employ parametric equations. Okay, so the picture for this is on the Cartesian coordinate x, y. We start from here, go like this. This is 1, this is 1. And the direction is given like this. Okay, so direction is, let's say, important just to pay attention to the direction. Okay, so if you change their places, for example, this would go in the other direction, but the arc will be the same. Another one is something like this. We have x equals t squared minus 2t, y equals t plus 1, and here t is all of r. Okay. Now, to understand this, we eliminate t from these. It's easy because I have just t here. T is y minus 1. Put it here. You have an equation in x and y. And it turns out that from here, eliminating t, we get, so the equation, let me see what the equation after we simplified is x equals y squared minus 4y plus 3. Okay. And when we draw this, the picture, the graph is something like this. So let me first draw this. And x-axis is somewhere here, x, y. So this point is 0, 1. This point is 0, 3. And direction is important. It turns out that this is moving in this direction. Okay. So for example, here instead of t equals r, we could give t equals some finite interval. Then you would check the endpoints, and it would give you only some part of this arc. Okay, so that's what we remember. Of course, a circle can be given with different parameterization. Generally, the way you choose a parameterization tells you how fast you are traveling along the path. Okay, so x equals cosine 3 theta, y equals sine 3 theta. This time, let's say theta is between 0 and pi over 6. Okay, so this is the same as x equals cosine theta, y equals sine theta. Theta is in 0 pi over 2, but the same arc is traveled faster. Okay, so again the same thing, but you travel it in a shorter time. Okay, one favorite curve of mathematicians is the cycloid. So cycloid curve is defined, the shape, or rather the curve, let's say, the curve followed by a fixed point on a circle which rolls along a straight line. So, for example, here we start with this circle. So let me use a different color for this circle. So this is the x-axis, this is the y-axis. Suppose this is our circle. We start with this circle. Okay. Suppose the radius is r, and we are interested in this point. Okay, so we are interested in this point, and this is the radius. Then we roll this along the x-axis. So suppose we come to some point here. This is again the circle. So this point, suppose now this is the new position. So I'll draw it something like this. This has to go up a little bit more. Okay, then it repeats like this. And we always measure this angle, theta. Here, theta is 0. Okay, so you roll this. So I keep this thing fixed to remind myself that I'm following this point. Okay. So you turn this around. So this goes this is one full cycle, then it repeats. Okay. So this curve is called cycloid, formed by circle of radius r. Okay. So it's parametric equations. From here, from this picture, you can find out the parametric equations for this. I will not go into derivation of this, but I'll just write the equations. The parametric equations for cycloid are the following: x equals r theta minus sine theta, and y equals r 1 minus cosine theta. And here you see theta is free. If theta is negative, we interpret it as the circle has rolled in this direction. Okay, so you have this red curve. You see that the reason why we sometimes use parametric equation is because parametric equations are sometimes more informative than Cartesian equations. In this equation, theoretically, you can eliminate theta. Okay, but after you eliminate theta, you are going to get a very complicated expression, because here you have theta all alone, then you have trigonometric functions of theta. To eliminate theta from this is, well, it's possible, but you don't want to. When you stare at that equation, you don't understand anything. Here, at least, it gives you some information. Okay, historically, this problem, this cycloid, was first studied because of its beauty. You see, it's an easy curve to describe. You can even write equations. Then you can calculate the area under it. You can calculate its arc length. To say that you can calculate them means that in mathematics, not theoretically you can find a number. You can find number for most equations, but the number turns out to be a simple expression of R. Okay. Then later somebody asked the question about the shortest time curve. Okay, so suppose, so consider this one. Okay, so here. So suppose you are skiing. Suppose you want to construct a ski path which is fast. Fastest between top and bottom. Okay, so this is your, suppose this is, mathematicians like to put a cross section. So suppose this is your mountain. Okay, now if you ski down, so we are modeling this, we say friction is too hard to calculate and its effect will be small. So let's approximate friction to 0. You are skiing from here to here only under the effect of gravity. Okay, so you calculate how long it takes for you to go from here to here. Then you consider a different path like this, and you check that when you ski down here, since this gives you acceleration, if there is curvature, it gives you acceleration. So you go from here to here along this path faster. So by playing with these things, you see that some paths are faster than the others. Then the question is, of course, what is the fastest one? Okay? So you can, of course, drop from here to here. It will be very fast, but then you are stuck here. You don't go. You have to give some curvature here so that it will push you over here. Okay, so it turns out that the answer is this curve. You take this upside down and put an arc of it on that part. Okay, so the solution will be upside down. Okay, so the fastest path will be given by an arc of a cycloid. Okay, so C this is the brachistochrone problem. Okay, go to internet and search for brachistochrone curve. So this is the Greek word for shortest time. Okay, chron is time. Okay, so shortest time problem. So it's solved by this. Another problem which was not related to this, but it's measuring time. Before the invention of smartphones, measuring time was a problem. So you want a cup with a ball rolling in it. Okay, so you want a cup like this. The cross section will be something like this. Okay, so it's supposed to be symmetric. So let me draw it again. Okay, so there is a ball here. Now this ball rolls here, goes up here, but while it's coming down, it cannot go up to the same point. It stops somewhere near to this and goes down, and then again stops somewhere lower than before, and it eventually dies. Okay. Of course, it takes a certain time to go here and come back, and next time it takes it shorter time to go here and come back because it's losing its altitude. Okay. Can I find a curve here? Of course, the answer is going to be brachistochrone curve. can I find a curve here so that no matter where I leave this ball, it will go and come back in the same time. Okay? So suppose this is something large like this. Okay? And I put the ball here, it goes and comes back in 5 seconds. Then I put it somewhere here. Obviously now, since the altitude is low, it slowly goes here and comes back, and it's still 5 seconds. Okay? So the answer is, again, an inverted and upside down cycloid curve. Okay? So we want to find the shape of the cup or ball such that the period of the ball is independent of its height, altitude. Okay, so the answer is again a cycloid arc. Okay, so if you draw an arc, a cycloid arc like this, so that will solve the problem. Okay, so historically this was studied first. I think Pascal studied this in detail and did all the calculations about this, and later on Bernoulli solved this problem. And then later it was discovered that it's, I think, again, I'm not sure who discovered this, but again, it was found that the solution to this problem is again cycloid. Okay? So that's why we always keep giving cycloid as an example. Okay, so another well-known curve is ellipse. We can give parametric equations for the ellipse easily, and in some calculations, the parametric equations are more convenient than the Cartesian equations. Okay, so I forgot the number, so let's say parametric equations of the ellipse given by x squared over a squared plus y squared over b squared equals 1. So this is, we mimic what we did with the circle. Okay, so this time, so this was unit circle, and if it's not unit circle, I will put r here, the radius. Here I put a cosine theta, y equals b sine theta, and theta is free. So you can turn around this ellipse infinitely many times, or if you just want some part of it, then you have to restrict theta so that it starts from one part and goes to the other part. Another famous equation is the following. So this is x equals t squared, y equals t cubed, and t is free. So when you eliminate t from these, you see that this is y squared equals x cubed, and its shape is something like this. So it is like this. And you check from parametrization that it is going like this. It is increasing like this. Well, this is famous because you see here we have a different point. If you stand at this point, suppose you are this very, very small ant, you stand there, you look around, and you think you are living on a straight line. Okay, so if you take this point, magnify it millions and millions, you will get something like this, and this thing looks like a straight line. Okay, so the curve looks like a straight line. Okay, so that's the basics of geometry. If you stand on a point, you look around and you think you are on a familiar space. Okay, so that's the local description of the geometric object, how these things, how you can pass information from this to the other guy. The other guy also thinks he's living on a straight line, but we have different coordinates. Okay, so that takes us to differential geometry and this is the basic concept of geometry. But you see, if the ant is living at this point, if he looks around, it's not a straight line. It's a different point. We call it as a singularity. So this is one of the basic examples of a singularity. Okay, but origin is different. We call such points singular points. Okay, and one of the main things is how do you recognize a singular point without drawing the picture? Because if you can draw the picture, there is no problem of recognizing a singularity. You just see it. But if the equations are complicated, so you see that now take the derivatives of these, then at t equals 0, both of them vanish. Okay, so that is the algebraic way of discovering that at this point is a singularity. There, you don't have a tangent vector because derivative of this is going to be a tangent vector. Okay, so that takes us to the subject of tangents. So,
Can you repeat how we determine the direction of the curve?
well, when you see, when t is positive, y is positive, and they are both increasing. So when t is positive, we are here. Because then t is negative, you must be here. Okay, now tangents. Okay, so suppose we have, as before, x equals f of t, y equals g of t. So we sometimes write this as position vector. Generally, position vectors are written as like this. F of t, g of t. This is position vector. Okay, so R is short for radius. Because classically, when curves were studied in R2 or in R3 in particular, at the point on the curve, you try to fit a circle there, okay, and you try to understand what the circle is doing. So radius comes from there, but we are not interested in that. We take the derivative of this, derivative with respect to the parameter of each entry. Then we call that v of t, so this is r prime t. And sometimes in physics, we like to shorthand do this like this. So this is f prime t, g prime t. And we call this the velocity vector. The velocity vector. The notation V is standard. Okay, so we will denote velocity. When you talk about velocity, we are all expected to write V. Okay, so this is a vector tangent to the curve at that point. Let us make this clear. Okay, so the vector is not, all vectors are at the origin. The curve is somewhere else. You see the curve is somewhere else in the space. I calculate a vector, the vector is here. So it is tangent, means that if you carry this vector without changing its direction, you put it at that point, then it will be tangent. Okay? Otherwise, this vector just maybe it doesn't even see the curve at all. Okay? So the picture will be something like this. Okay, so example, if x equals cosine t, y equals sine t, so we have rt equals cos t sine t, v of t is minus sine t cosine t. So the picture is something like this. This is our curve. Okay, So this vector is r of t, and this vector is v of t. Okay? So if you carry this vector here, okay, so you can, when we are trying to understand the geometry or physics of this, we write the vector v here, vt. Okay? We write it here, but algebraically means that when we are doing calculations, it is actually at the origin. Okay? So this is not a big idea, but when you are doing calculations, it helps. Okay? So, sometimes the vector the vector pointing to that point and the vector pointed to some other place, sometimes we get confused whether they are tangent or not. So this is what we mean when we say that the velocity vector is tangent to the curve. Okay, so okay, we have the cycloid also, cycloid example. So the cycloid position vector was this, r theta minus sine theta, and r 1 minus cosine theta. So its velocity vector will be, okay, so let me just write it here, r 1 minus sine theta and r sine theta. Okay. So from here, for example, you can answer questions about when the vector is parallel to x-axis, when this is parallel to x-axis, etc. Okay, so I'll skip those things. And okay, so okay, let's come to the usual calculus now. In usual calculus, we are interested in the slope of the tangent line because that's where our calculus leads us. So slope of the tangent line. So this is actually always dy over dx. Okay. So let's see what we want to say about this. Okay. When parametric equations are given, we have v of t. This is the first part is you take the parametric equation of x and take its derivative with respect to t, like we did f prime, g prime. And the other one is dy dt. So from here, we want to recover dy dx. Okay? So in this example, so this dx, dt, dy, they behave as if they are independent numbers. They cancel. So if you divide this by this, that cancels. But only in this example. For example, when you want to find the second derivative of y with respect to x squared, then if you do cancellation, you get a number which has nothing to do with the second derivative. Okay? So that these things behave like as if they are canceling in this particular example is not because they are independent, but it's because of chain rule. Okay? So by chain rule, dy over dt is dy over dx times dx over dt. Okay? So in the expression, I know this, I know this. So from here, we have dy over dx is equal to dy over dt over dx over dt. So again, let me repeat that. In this example, it acts as if we canceled dt's, but if you now write the second derivative of this with respect to x, the expression you get will not have any suggestions about cancellation. Okay, so the reason this worked is because of the chain rule. Okay, so we have a few more things. So I have to refresh our memory about arc length. So with arc length, let me draw a picture because that's the crucial picture in arc length. In calculus, the main philosophy is you approximate something with things that you can easily calculate. You make an error, of course, and if you can control the error and if you can show that the error goes to zero when you make a finer and finer approximation, then you get a formula. Okay, so that's almost all the formulas in calculus are obtained in that way. For example, integration or arc length. So in arc length, this is the approximation we make of a curve. So suppose we have a curve like this. Okay, so this is y, this is x. At this point, okay, so suppose this is x, and suppose this is x plus delta x, assuming delta x is positive. Okay, then we have this part. Now this distance is delta y. Okay. It is easier to calculate, however, the following thing. Here you consider the tangent line. And this distance, this red distance is, okay, so this distance is, we call it dy. That's how much the tangent line will take you at that point. Here you calculate the function. Here you calculate the value of the tangent line. Okay? Now, arc length means we are trying to approximate this length. Okay, so we are trying to approximate this length. Okay, so we can do it either by finding this length and saying that this is approximately equal to this, or we can find this length and we say that that's approximately equal to that. So this one is easier to calculate because all the information for this length is given at this point. I have the value of the function there, which means that I know the coordinates of this point. I take the derivative, I know the slope of the curve at this point. You know the slope, you know this point, so you have an equation for this line. So you can calculate the value of a point anywhere on this thing. So you calculate the value here at when x is equal to x plus delta x. Okay? But in order to calculate this, you have to evaluate the function. Okay? So function is not generally linear, but when you are evaluating the line, it's easy. Okay? You just put x is seen only at one point and to the power 1. Okay, so the green arc length is approximated by the length of the green part of the tangent line. Okay, so at this point, if we approximate it with this second line, we will get exactly the same formula, but then it doesn't generalize to higher dimensions. For example, when we try to calculate the surface area is not an approximation of the planes that touch it or cut it, like a generalization of a secant. That doesn't give you the surface area. You calculate a portion of the tangent plane. And which portion? Okay, you go a little bit in the x direction, you go a little bit in the y direction. You get a square. On top of the square, you look at the area, the area of the tangent plane. Okay, so that's the way these things generalize. So at this point, it is better to consider this one. And of course, by taking delta x small, the error is small. But then if I'm trying to calculate the area, say from here to this point, if I take delta x is very small, I'm doing many approximations. At each approximation, I have make an error. I'm decreasing the error, but I'm increasing the amount of time the times I'm making errors. Okay, I decrease my error, but I have million more errors. It turns out that in this case, as you increase the times you are making an approximation, the sum of the errors go to 0. Okay, so that's why we have a formula. So you add these approximations and take the limit as each delta x becomes smaller. You get a formula. Okay, so arc length. So generally we call it by L and sometimes S. So this is from 0 to, okay, from A to B of 1 plus dy dx square dx. Okay, so here if y is given as an equation, y equals f of x, and x is in the interval a, b. Okay. So when we do this parametrically, so this is when the curve is given as a function. Okay. So when we do this parametrically, since with one variables these t behave like canceling, you can guess what the formula will be. Okay. And then you check if that formula, the formula you find by ad hoc methods really works. Okay, so it really works, and I'll write the formula. Okay, so if, however, the curve is given by parametric equations, okay, then we have to change things. Okay, so again using chain rule as before. You see, we are trying to understand this part. Okay, so this is the part we want to understand. Okay. So what we have is the following: 1 plus dy over dx square dx. Okay, so this becomes, so what do I want to do? I get this dx inside, so this will be, okay, so this part I'm putting an exclamation mark, seeing that this works, but I'm not going to explain why it works. Dy square. Okay, now divide and multiply by dt over dt. So dt, this is 1. Okay, so what you have here is dx dt squared plus dy dt square dt. And you see that this time this is equal to length of the velocity vector. Okay, so these are the x and y components of the velocity vector dt. Okay. So what does it say? Arc length is given by integrating the length of the velocity vector. So this is what we did incrementally. Okay, incrementally means that we don't know exactly what it means, but we are doing it on a very small interval, and we are hoping that the errors will go to 0 eventually, and you check whether the errors go to 0 or not. But that's not done in calculus. We just borrow this from advanced calculus where such things are explicitly done. Okay, so at this small interval, you see, I look at the length of this vector, this tangent vector. I add up all these tangent vectors. So next time I am here, I draw another tangent vector and calculate its length. So I add these things on very, very small intervals. Well, that's a polite way of saying that I'm integrating this length over the whole interval. Okay, so arc length equals, well, the parameter is now starts, say, from alpha to beta. So let me say t starts from some place, and then I look at this dt. Okay, so let's calculate this arc length of one turn of cycloid. So the circle turns once. So from here you see theta starts from 0 and goes to 2 pi. Okay. So here remember that x was equal to r theta minus sine theta. Question? Bir şey mi var? Yok. Okay. Y equals r 1 minus cosine theta. One turn means that we are interested in theta 0 to 2 pi. Okay. Now length is equal to from 0 to 2 pi square root of the velocity vector. So I'll take the derivative of this and take its square, r 1 minus cosine theta square, plus I take the derivative of this r sine theta square d theta. Okay. So you calculate this. Well, inside you get something nice. So square root 2 times r from 0 to 2 pi square root 1 minus cosine theta. Okay, so 1 minus cosine theta is sine square of half angle multiplied by 2 or something. So, okay, so you can use half angle formula. And you get 8r. Okay, so I'll skip the integration details there. Okay. Okay, so let's see what else I want to do. Okay, so on Thursday I'll take 5 minutes to write the same equation, explain that the same equations hold in 3 space. So you see that when we reach to this formula, there is no dimension restriction here. In whichever dimension you are, in calculus we will be either in R2 or R3. The length of the velocity vector is well defined. You integrate the length of the velocity vector and you get the length. So on the first 5 or 10 minutes on Thursday, I'll do this and then we'll start the new chapter.